Check, check. Check, check. All right, you can hear us online. Fantastic. Well, kia ora, everyone. Welcome to Oricon. Please grab yourself a drink, grab yourself a bit more food. Come grab a seat, and we will be kicking off in just a minute or two.
If there aren't quite enough seats, feel free to grab a stool from beneath the tables at the back. Okay, welcome everyone to the first Auckland Bridge Group event, probably in the last 5 or 6 years, which is pretty cool. Today we're going to have a presentation on Te Ahua Turanga with the 4 presenters at the front here. I'll just go through a few housekeeping items first. So if you need to go to the bathroom during the event, you'll need to use the bathrooms on the next level up, which just go up the timber staircase, and then they're on the left-hand side past the lift. If you do leave this area and go into the other bathrooms, you won't be able to get back in. So try not to do that. Fire exits, there's 2 fire exits. If you could just follow this green sign here and go down that avenue, or the way you came in past the lifts, there's also the same signage. So as I said, this is the first Auckland Bridge Group event in a number of years. We'd like to thank CSOC for sponsoring and providing the refreshments this evening. The intent is that these events will be quarterly and that they will tie in with the Wellington and Christchurch groups. As part of that, for future events, if anyone has any ideas for presentations or would like to host an event, please contact one of these people on the screen. This is the steering committee that we've set up. And if anyone's interested in being a part of that as well, please reach out and let us know. I've also got a brief plug for some University of Auckland research that's happening. The PhD student that's doing that is seated here at the back. He is doing research on bridge inspections with UAV and virtual reality. So we'll be sending out a follow-up email in the next few days about this to try and get people involved who are keen. So then getting on to the main event. So we've got these 4 speakers tonight: Bill, Jack Chai, and Sam. So I'll welcome up Bill to get things started.
Thank you, everyone, and it's our great pleasure to be able to present to you tonight. And I think as engineers, we're often quite fixated in solving problems, doing designs, but quickly we move on to the next thing without much reflection. So, but I think when you start reflecting, you realize the massive challenges that you face on a project and also the challenges that you overcome. And this project is no different. So thank you, Kim, as well as the Auckland Bridge Group for inviting us. And we're excited to share with you some excellent engineering work and also some lessons learned. And yes, I'm joined here with my more esteemed colleagues, Jack, Sam and Jack Chai, and they'll introduce themselves more later on. I'm Bill Van. So, an overview of the project. So the bottom of the North Island is split right down the middle by the Ruahine and the Tararua ranges, as you can see in the dark green strip right down here. You can't see my mouse, can you? Okay. And right between them is the Manawatū Gorge and the Manawatū River. Historically, State Highway 3 runs alongside the Manawatū River and provides a critical connection between the east and the west coast. But there's a bit of a problem. Landslides. There has been quite a few landslides in the past, which closed down State Highway 3. And in 2017, it was deemed that it was no longer safe or a resilient route for what is quite an important asset to the bottom of North Island, and hence the need for this project, Te Ahua Turanga. So this project is to replace the old State Highway 3. The new route now runs along the top of the northern side of the gorge. There's a number of structures on the project, but the two main structures we'll be looking at is the Parahaki Bridge over here and the Eco Viaduct over here. So the site also poses quite a few challenges. For example, we are in a region of very high seismicity. There is the mighty Manawatū River, which runs underneath the Parahaki Bridge. And also it is very, very windy. So this is just an artistic render of the Parahaki Bridge. So it's a concrete box girder cast in situ. Overall, it has a length of just shy of 300 meters, and it has 3 piers. And also there is the Eco Viaduct. But I'll pass you on to Jack to talk about his bridge.
Thank you, Bill. Kia ora, everyone. Jack Manners. I'm a bridge engineer here at Oricon, and as part of the Te Ahua Turanga Alliance, I worked on the substructure design of Bridge 3, or Eco Viaduct. Fairly brief presentation this evening because we've got a lot to get through, but I'll give a broad overview of the design before giving a little bit of depth into the seismic design and philosophy, how we designed for reasonably uncertain ground conditions through the design period, and then touch on one of the key features, which is the integral pierhead design. So I get this question a lot, Eco Viaduct, why the name? So the site and the alignment through this area passes through both an ecologically and culturally sensitive zone. On the western edge of the alignment, which is the left-hand side of the image, is an old-growth forest of native trees. The southern side of the alignment has both a swamp mairi and then a raupo wetland. Historically, this was a mahi ngā kai area, so an area of harvest for the local iwi, and the iwi were project partners as part of the alliance. So these kind of site constraints, some of them legislated in planning, drove the solution for a viaduct. I get a lot of questions around whether this is a low carbon bridge design. Yes, in some ways, but that's not the driver for the name Eco Viaduct. It's to reflect the site that it takes the new State Highway 3 alignment through. So specifically on the bridge, 7-span structure, 305 metre total length. The 6 main spans are 47 metres long and has 2 back spans of 35 metres. Geometrically, it's on a vertical sag curve, and there's a super elevation transition from the south abutment to the north abutment, which posed a few design and construction challenges. The structure carries 2 lanes in both directions, 2 traffic lanes, as well as a shared use path, which is attached to the eastern side of the bridge. The superstructure, which I'm not touching on in too much detail in this presentation, consists of 1.8 metre deep weathering steel eye girders as brace piers, and it's made composite with a reinforced concrete deck, which is made up of precast panels and an in-situ topping slab. The piers are integral, as I mentioned before. So we've got a reinforced concrete headstock supported on 1.8 metre diameter reinforced concrete piles, columns, and 2.1 metre board concrete piles. The articulation at the abutments is on sliding pot bearings and some fairly large modular expansion joints. So the seismic design, haven't got a whole bunch of time. I could talk about this for quite a while, so I'll give a pretty brief overview. As Bill said, area of really high seismicity, which is the kind of key challenge for all structures on the project, and earth structures and slopes included in that. The spectra design, the acceleration design spectra shown on the screen. The green curve is the site-specific design spectra we use for the design of Bridge 3 and Bridge 2. So that's the 5% damped spectra. And for context, the black line at the bottom of the graph is the equivalent importance level for a similar structure designed in Auckland. So significant seismic loads. Obviously, the spectra is further reduced depending on specific structural damping at each bridge, and I'll talk a little bit around that for Bridge 3. So Bridge 3, ductile design, fairly typical seismic philosophy. We've designed it to form plastic hinges at the top and bottom of the columns highlighted on the screen there. And one of the points of Bridge 3 was that the minimum requirements for the job stipulated that it had to be designed for the worst case of both the displacement-based design methods and the force-based design methods. And I think this was possibly a product because this was one of the first projects to be designed to Bridge Manual version 3.3, where, as most of you will understand, was the first time that displacement-based design was fully incorporated into the code. So it was an interesting exercise on a real project to compare the two methods. Like I said, can't go into this in too much detail, but a few kind of key overview points. So the target displacement transversely under the displacement-based design method was 470 mils transversely at midspan at the DCLS strain limits. Depending on a bunch of factors, including stiffness and geology, the global ductility of the structure under that case was approximately 2.9 to 3. The image out of the analysis model just shows an excerpt from the Midas nonlinear pushover analysis, and we use that analysis method more as a confirmation of the force-based approach, but also to determine the overstrength actions outside of the plastic hinge zones, particularly at depth in the piles. There's just a couple of images from the construction drawings of what we ended up with in terms of seismic detailing. Fairly typical. It's what you would expect for a structure of this type, a 2-column bent ductile reinforced concrete design. I guess the difference from other designs I've worked on is just the scale of the loads and the magnitude of the loads in the columns and piles, which led to quite high reinforcing percentages and a lot of confining steel. I won't dwell on these details too much. So like I said, we did design for both force-based design and displacement-based design methods. I'm sure the images on the screen are familiar to a lot of people from Priestley's book, The Displacement-Based seismic design of structures. Bridge 3 really is the case study bridge for a displacement-based design approach. We've got varying column heights and varying stiffness along the length of the bridge. And so it really lends itself to a displacement-based design. And what we found through the process was the force-based design generally gave 5 to 10% higher bending and shear actions than the displacement-based design. And while that increase doesn't drive a totally new solution like a step change in pile size or column diameter, it does increase reinforcement, increases congestion, and probably most notably for this structure, because of that demand, the overstrength actions really shoot up in the adjacent elements to the hinges. The other one of the other key challenges for Bridge 3 was what I'm terming designing for geological uncertainty, which is not uncommon on bridge projects, but I think was particularly uncertain for this structure. The image on the screen shows the investigation plan for the bridge. The red dots were the existing boreholes we had prior to design. The green dots were the planned investigations by the Alliance, and the orange ones, which broadly follow the alignment, were proof bores to be done during construction. So as you can see, not many red dots around the bridge site itself, and we had issues with both pandemic restrictions and then weather events to prevent us doing the green planned boreholes investigations throughout the design process. So we essentially designed with very limited information all the way through to all the way through the detailed design process. And as we came through and completed some of the investigations later on in the design, we encountered quite high artesian water pressures, which Sam's going to touch on in his presentation, which drove a couple of changes in the design, but won't go too much into it now. But generally, this is the ground model that we were dealing with. So 3 kind of broad materials. The main image there is a long section along the bridge site. So on the southern end, the yellow material is superficial, some organic deposits, which very soft material, not very well, not great material. The main rock sequence is the Te Apati sequence, which is both weathered and unweathered rock formation, which we're founding the bridge on. And at the northern side of the bridge, we have these siltstone marine sequence deposits. But because of the limited information that we had, limited investigations, we really didn't know exact depths or I guess the interface of these kind of 3 main sequences. The other key feature is the existing Raukaba fault, which broadly runs north-south along the alignment, crosses over at one point. The fault is assessed to be non-active through the design process, but as you're aware, at fault locations is where we tend to get quite large steps in the stratigraphy. So the cross sections, which are shown on the right-hand side of the screen, show the kind of predominant slope of the geology through here. And one thing we didn't really have a good feel for was the angle of that slope. And so rather than just what we would typically do for the sensitivity of geotechnical conditions, we had to do a little bit more to satisfy ourselves that the design was adequate. And so what we did was, rather than just a spring material sensitivity, we did a sensitivity of stratigraphy, where we assumed both the upper bound, or the shallowest conceivable rock head, and the deepest conceivable rock head. And that essentially gives us the stiffest response and the softest response. On top of that kind of broad category, we also applied material sensitivity. So that ends up in a lot of models, a lot of analysis, and a lot of rework if you make one mistake in one model, or you discover one mistake in a model. But I think it was a good way to mitigate, I guess, the increased risk that we usually have in terms of geology and uncertainness. The last thing I'd like to talk about is just the integral pair. it's a key design feature of the bridge, driven for two key outcome areas, which is low maintenance design, and as discussed earlier in the presentation, this is quite a sensitive area, and so we're trying to eliminate or minimise the amount of access, particularly from the ground, to the piers. It also is driven by the aesthetic outcome of the bridge and trying to minimise the overall depth of the bridge at the pier locations. So integral piers aren't anything new. They're becoming increasingly common in New Zealand and are common definitely overseas. But typically what we do is we form these in a two-stage pour. So we will pour a concrete headstock element as stage one, land girders, superstructure on top of it, and then cast it integral with a secondary pour. For bridge 3, we essentially eliminated the bottom half of the first pour, and so we poured this as a single stage pour. So that minimises the concrete depth and overall material below the bottom flange of the superstructure, which gives a really neat and unique aesthetic look to it, but does pose some design challenges. Our thinking for this connection definitely progressed through the design process. So at 50% design and earlier, we had a solution as shown on the screen where we had assessed that the top flange of the eye girder remained permanently in tension and the bottom flange was permanently in compression. So our solution was to take the compression out of the bottom flange through a bearing plate, which eliminated the need for a full splice. And I guess the key benefit in terms of the substructure and the superstructure design of that was it frees up that middle section of the headstock to be used as continuous structural concrete element through the length of the pier. But as we progressed analysis and off the back of some of the geological modelling that we did, we couldn't convince ourselves that under all seismic low cases that the bottom flange remained permanently in compression, and so we needed to provide a full splice through the headstock area. This introduces a lot of additional steelwork through the headstock, a lot of bolts, and a lot of shear studs, and it also removes that continuous concrete element that we previously had running through the centre of the headstock. So that poses some design challenges, and the key challenges are: how do we take global shear out of the girders and into the columns? And the same thing with global torsion. The headstock is disrupted by the girders as they pass through the concrete section, and so we need to satisfy ourselves that we had a feasible load path to take load out of the girder, particularly the inside girders across the girder adjacent to the column and into the substructure. So for global shear, essentially the philosophy was to take the vertical load that exists in the girders out through both shear studs located on the web, as well as passing bars through the web, which are clamped onto the web using a flange nut through shear friction. The flange nut, which was quite a unique solution, allows us to adopt a higher coefficient of friction in order to take more shear out through those bars than we would just passing bars through a slotted hole. In terms of the concrete section, we essentially assumed the section as a series of depth beams, and that was analysed through a strut and tie model. So locally reducing the height of the concrete section as it passes through the girder section under the flanges. Global torsion, similar problem. We've got to get the torsion that exists in the headstock across these across the girders. So typically we allow a torsional flow path around the perimeter of the concrete unit, obviously that flow path is not valid once we put a beam continuously through the section. So what we did was a similar philosophy. We're taking the bending stresses that exist in the flanges out through shear studs, which are located on top and below of both of the flanges. We then have drag bars, horizontal reinforcing drag bars through this kind of, we've imagined as two 500 deep concrete sections, which act in out of plane bending to take the bending stresses from the shear studs into the concrete section, rather than a full tubular wall flow path that we would typically do. In terms of the design outcomes, because of that, a lot of reinforcement. So we already had a lot of reinforcement in the headstock due to the overstrength actions based on the hinge at the top of the column. On top of that, we add a number of quite unique bars. So a huge number of shear studs to take out both vertical and bending stresses, as well as bars passing through the girders with flange nuts. So a very unique solution, a lot of reinforcement, which I'm sure Sam will touch on as part of his presentation. But I think all in all, developed a very unique solution that address the site constraints and objectives for the bridge, and has led to a really neat outcome aesthetically, now that you can see them being constructed, and Sam's got some photos of them later. That's all I had for Bridge 3. Happy to take any questions at the end of the presentation, but I'll now hand to Jack Chai to take us through Parahaki Bridge.
Hi everyone, I'm Jack Chai, bridge engineer from Oregon. So I'll be covering Parahaki Bridge today, which I think, let me go to the first slide. Okay, so I think Bill already introduced us the overall arrangement of the Parahaki Bridge, which I wouldn't repeat it. I just want to add on one other thing, which is about the substructure scale compared to the superstructure scale. So the pier column is varying from 19 to 25 meters from pier 1 to pier 3, and the box girder itself, typical width is around 25.75 meters, which carry both the traffic lanes and the chase path. And you know, in the plan view, the bridge is constructed on the horizontal radius of about 725 meters and on 1% vertical grid. Okay. Next thing I want to touch on is about the seismic design criteria and inputs for the bridge. So the bridge design life is 100 years in accordance with the bridge manual. We have adopted the importance level 3 for the bridge. Our main compliance will be similar to Bridge 3, which is the bridge manual amendment 3, third edition. But also we adopted the AASHTO guide specification for isolation design, because the bridge is proposed to be base isolated structure. And DCOS event earthquake, the RU is taken as 1.3 at 1,000 year return period. And typically for collapse avoidance limit state, it would be 1.5 times the DCOS, and for SOS would be quarter of the DCOS. Next thing is about the seismic loading for the substructure. In our project, as Jack mentioned, we have the project site-specific seismic hazard study, and it is in the form of a spectra. We use that for the SLS analysis, which is the response spectrum method. For the DCLS and CLS design, which involve in designing the lead rubber bearing, we use the ground motion records via the nonlinear time history analysis. So this slide here, I just put a snapshot, which the table here is the ground motion record input that we receive from the EGL, which is Engineering Geology something consultant. I can't remember, sorry. But basically, we have a total number of 7 records, and each record has been scaled and selected to be appropriate to the conditional spectra for the project. You can see here that record, I think, 3 to 5 has the directivity effects, or we call it the forward directivity. This is to reflect the fact that the bridge is located in the proximity of the active fault, and basically within 20 kilometers, and therefore the near fault consideration need to be considered. And also the 1170.5 earthquake standard require 1 in 3 of the ground motion to have the forward directivity effects. So that's why we have that. And then I just want to let you know that I will not touch on the detailed nonlinear time history analysis today because of the time limit. But I just want to point out why we propose to use the nonlinear time history analysis for the bridge. So first of all, the bridge is located within the 10 kilometer of 2 faults, which we don't really know the final status of the fault, which is going to be active or not, but we assume it to be active. And I think in early stage of the design, we understood that the site condition can be a soft soil site. And the last thing is we want to understand the detailed dynamic behavior of the isolator, which we can understand the loading history and review the design outcome of the isolator better. And last thing is about the structural period as well. Normally when you provide the base isolation, you expect your structural period to shift, and we expect it to be around 3 seconds. And based on the international code of practice, it is suggested nonlinear time history analysis method is the appropriate one to use. Okay, next slide. Yeah, so next one is for the seismic design philosophy for the bridge. So in the SLS earthquake limit state, we expect no damage incurred to the bridge structure, and basically the bridge will be serviceable during the earthquake event at the service limit state. Next one is the damage control limit state, which I think I put the word low damage design approach. So basically we want to design up to the design earthquake event. We are proposing the bridge to be base isolated so that the level bearing can dissipate the earthquake energy, so that it will reduce the seismic demand, so that the substructure can be designed to remain elastic and therefore no repair needed at the design earthquake event. So at the collapse avoidance limit state, we expect the bridge to respond in the limited ductile at the maximum design displacement of the isolator. Basically, the design may allow some inelastic response of the pier column, which can be accessible for repair after the major earthquake event. I think I should go to the next slide to give everyone the overview of the substructure system. So before I come back to the design philosophy, so the abutment is the shallow footing foundation sitting on the preparation of the geotechnical subgrade, and the abutment is 6.5 meter wide by 2 meter deep, and the total width of the abutment to carry the box girder is about 26 meter, as you can see on the screen. And on the left bottom image, that one show the proposed translational fixity for the bridge. So this element here will be provided to certify the SLS earthquake event, such that we call it the shear key, or the fungible guided bearing, will be taking up to the SLS earthquake demand, and this thing will start to the bulk group that you can see on the just on underneath the horizontal steel beam will start to be sheared off, and then allow the level bearing to displace for the earthquake event beyond the SLS limit state. Next one is the pier system. So the pier system is the cantilever reinforced concrete column. The pier shape has an oblong like cross section and this hollow core section. But the top 2 meters of the pier is solid section to support the lead rubber bearing and also the superstructure on top of it. Then the pier column will be supported on top of the 14 by 14 meter and 3 meter deep pile cap, which then, sitting on the 8 number reinforced concrete board pile. And the diameter of the pile is 2.1 meters. And I think Sam will touch on this in the challenge during construction, but you can see at the pier 3 here, we need to rotate our pile cap quite a little bit, but yeah, about 39 degrees, which make it irregular. We did it because we want to ensure that the clearance to the hazard inner zone to key rail can be achieved, and it has to be greater than 10 meters. Okay, so this slide here is the main thing that I would like to cover today, and it is about the base isolated structure. As I said before, we propose to use the lead rubber bearing isolator as a primarily earthquake load resisting system, and basically how it works is like the isolator is much flexible than the deck itself, and therefore when there is a seismic excitation, all of the movement will try to be occur in the isolator, and because of the lead and the elastomeric rubber material, the lead will undergo the plastic deformation, which the energy will be dissipated through the vibration mechanism. And when this happens, there'll be the additional damping added to the structure, which more flexibility. And then you can see on the right top hand corner that the structure period will be shifted, which means the acceleration demand from the earthquake will be reduced at the same time. For the components of the lead rubber bearing, so we have the lead core, which acting like a damper or the energy dissipation device. The rubber layers, this layer, the rubber provide a lateral flexibility to the structure, and then the steel plate layers, which provide the vertical load carrying capacity. And the cover rubber will be providing the protection to the steel plate inside. And then last thing is the mounting plate, which, connecting to the lead plug and the rubber to provide a load transfer to the substructure or the structural element that it connects to. Okay. Yeah, so this just not quite challenging, but just want to give everyone overview like what we have to consider in terms of designing the lead rubber bearing. And I only put that equation on top, and this equation was extracted from the AASHTO guide specification for the isolation design, but I will come back to this equation at the end of this slide. We should look at each bullet point here that I put. So what we want to make sure our design is capable of resisting the maximum shear strain that occur to the isolator. And I just want to give a commentary on this. I think in the bridge manual, it said that under earthquake event, when you use the elastomeric bearing or lead rubber bearing, you shouldn't exceed, I think, 100% shear strain. But then from study of the International Code of Practice, there was some other limit, which is like 200% shear strain and up to 250% shear strain. So in our project, we propose our limiting shear strain to be 250%, 250%, and at the maximum desired displacement, which I will touch on this at the end of the slide, why we think that this is achievable. And then the rotational capacity. This one again, the formula to check or to understand the rotational capacity is quite straightforward. Just one thing to note of is you need to consider the construction tolerance when you add the rotation demand to the equation. So basically, the number is like 0.05 rats that you have to consider for the construction tolerance for the rotation demand. And then the axial compression load capacity. So I think the way to calculate the axial load capacity is straightforward again, but you need to consider the rated load at the corresponding shear strain, which would reduce your axial capacity. And also there's a risk of the buckling of the bearing under high axial and then at the maximum shear strain as well. So we have to consider that as well as part of the compression check. Next thing is lateral restalling force. This one here is basically like a check to ensure that the cumulative displacement of the isolator can be like limited, and also to accommodate the isolator installation imperfection as well. So it has been checked in accordance with the code. And then heat effect under cyclic response. As you can imagine, when the lead plug start to yield and then start to displace in the plastic lay deformation, in the reverse cycles, you would expect the energy to display through the vibration, and also at the same time there be rise in the temperature during the excitation of the lead plug. One thing to note is that it depends on your loading history and number of the fully reverse cycles that you would expect for the earthquake ground motion record that you input into your model. It's based on some if the temperature that rise in the lead plug start to be quite high, you may want to like flag this up or talk to your manufacturer of the lead bearing, like what is the limit of temperature that may impact the capacity of the lead plug, which mainly it will reduce the yield load of the lead plug when that happens. This one I suggest to look at the Priestley textbook. He has written some good recommendation about the heat effects of the lead plug. And last thing is the tensile strain. So the tensile strain, from my understanding, there is no such a limit on the code. And it doesn't mean that you have to do it or you can allow some tensile strain demand. It was actually written to the way that you shouldn't design your bearing to have tensile demand happen. So therefore I put it, it is beyond code of practice, but I'll touch on the key finding later. Okay, so this slide here, just to give everyone the overview, what we have to say consider as part of the next step, which is modeling of the lead rubber bearing. So we need to understand and coordinate it with the supply as well. What is the material for the lead core? For example, shear modulus, and the U shear strength, the rubber shear modulus, and the elastic modulus of the rubber, and also the number of layers that you see here and the layer thickness. This thing need to be well proportioned to the lead plug diameter, so that when you got the result from your analysis, then you calculate those limited shear strain demand. It all contributes to the last equation. And these material properties that I put here, I think they are quite typical and they're accepted in the industry for the lead rubber bearing. Okay, so in terms of the key modeling, so we have to consider maybe 4 primary components when we model this into the structural model. One is the nonlinearity properties in the lateral direction, which basically our design proposed to use the idealized bilinear force deformation relationship, which you can see on the top right hand corner, which is taken from the Astro standard again. So basically we have to consider the initial stiffness, which is the stiffness of the elastic lead and also elastic of the rubber. And then once the yielding of the lead happens, So it will change its stiffness to the KD value that you can see at the top right hand corner. This stiffness will be just the rubber itself alone. So for the vertical direction, the way to calculate the compressive stiffness is straightforward, and this can be given by the suppliers as well. One thing that we have put into our modeling is that we also tick off the box for the nonlinearity effects of the vertical direction, which means that we expect that the bearing may go into tension as well. But I put the magic number as 1,000 here. It looks like a magic number for now, but I touch on it why it becomes the magic number with the 1,000 kPa, which is 1 MPa. And then the rotational stiffness, this one is simple and just calculated in accordance with the AS5100.4, which is the bearing standard. And last one, so we have to consider the lower bow and upper bow properties of the bearing. The lower bow will be the nominal characteristic value, which is the QD value, the characteristic strength, which I put in here. And also the stiffness will be multiplied by 1 as a lower bow. But when you consider upper bow limit state, I think there are a few ways to obtain this throughout the code. Also get it from the manufacturer. But in our project here, we were lucky that we have the lead rubber bearing specialist. I think his name is Ron Mayes. So we adopted the upper bow properties, 1.15 for the QD and 1.4 for KD based on his recommendation. Yeah. So that I think I have covered the key modeling that we have considered. This slide here, I just want to talk about it 10 seconds. So I'm not trying to get everyone to read through the graph that I put here, but I just want to say that from now on, I will present some key finding. And the key finding, when we obtain the displacement from the model, we have to average it across the 7 records that we input into our structural model. So basically, as you can see here, the design displacement will be the averaging peak response over maxima and minima over the 7 records that we have. So the first key finding, yeah, I think we have run the model. We have to consider soil structure interaction as well, like what typically we have to do, and we have to also consider the lower bow, upper bow property of the bearing, and for the maximum desired displacement of the lead rubber bearing in our bridge, we got it to be around 955 millimeters, and with the corresponding axial load of about 6 meganewton. So after we obtain the desired displacement, make sure that it does work from the supplier side as well for the size. And then we can calculate the effective isolated structural period at the collapse avoidance limit state, which is 3.2 seconds. And then the energy dissipation per cycle, which, yeah, 4.5 kilojoules, like 4,500 kilojoules. And then calculated rated axial capacity at the maximum total desired displacement, which is about 40 meganewton per bearing. So we are beyond the capacity is beyond the demand. And this one, we also note that the average peak total desired displacement for across all the bearing averaging is about 0.88 meters. So our critical design will still be the 955 millimeters. This one here, just to prevent some, boring, I just found out that in the structural model, in my DAS civil, that's what we use for the time history analysis, it can produce some like a good looking animation, so that when you muck around with the numbers too much, you can just save this animation to watch sometimes. So I just give it a view. This the response under the collapse avoidance limit state at the one of the record, which is oriented to the longitudinal direction. That's it. It helped a little bit. Okay. So the next key finding. Yeah, so as I said before, about that magic number 1000 kPa, which is like 1 MPa. So these two tables here present the maximum and minimum vertical reaction for DCLS and the CLS event. Let's touch on the DCLS first. So at the peer 2, you can see that the negative sign means compression, positive means tension. So at the peer 2, we pick up one of the bearing pair has the tension demand into the bearing. So we hope it did not happen, but as it happened, we justify that we calculate the tensile stress based on this tension demand, and it's about 0.25 MPa. And also the tension demand occur at only one pair out of all the lead level bearings in the system, which we have about 26 bearings in total. And also we can equate the tensile stress demand into the corresponding uplift deformation, which is about less than 2 millimeters. So based on all this understanding, so we justify that the chance of the structure to be unstable during this less than 2 millimeter uplift of just one pair bearing is not likely, and we are confident with our design on this. And then at the collapse avoidance limit state, we found that as a few bearing pair went into tension, where at peer 2, we have the maximum tension demand of 2,710, but this demand here has to be divided by 2 because we have the result as a pair. And from this demand, we equate it to the stress, and the maximum tensile stress is about 1 MPa, with the corresponding shear strain of around 50%. So we justify again to accept the tension demand, given that this will not cause the collapse to the structure. So our justification is based on the review of the nonlinear time history results, and it was found that this magnitude of tension only happen in a fraction of a second before it turns into another pattern. And also we have studied a few technical references, including the New Zealand Society for Earthquake Engineering, and normally 1 MPa tensile stress demand wouldn't impact or even change the characteristic values of the lead level bearing, and therefore we don't think that the bearing will be affected in terms of the integrity of it after the major earthquake event. And last key finding that I want to present today. So we have also conducted the sensitivity check around the friction coefficient, because our abutment pad is sitting on the is shallow footing and sitting on the geodetical subgrade details. And basically we want to test the sensitivity of different coefficient of friction. So it has lower bound limit state and upper bound limit state. So our lower bound limit state for the project is 0.6 for this bridge. And then we also tested for upper bound value of 1. The reason for this test is one of the case may produce the more displacement to the isolator. However, after conducting the analysis, we found out that the isolator displacement is not highly sensitive to the variation of the coefficient of friction. But again, when you think about the substructure action, you would expect that the lower bound coefficient of friction would produce more action to the piers and the columns and the piles, because less coefficient of friction would have less amount of the energy dissipation, less sliding resistance. And my last slide, So I just want to cover on the seismic performance verification. So once we have finished with our proposed design, we also want to ensure that the lead level bearing configuration that we propose is going to work, and this is going to be done via the verification testing. And we base our verification testing on the ASHTO specification again. So basically, we have to test for a sustained compressive load, wind and braking test before and after the seismic event, stability tests, and wear and fatigue tests. But I won't go too much detail into this. I just want to turn on the video and show you how it was done for our project. Okay, that's it. So basically, it is the test at the second cycle, and the bearing was tested to display it up to the collapse avoidance limit state displacement, and it still look okay, which I'm happy with. And yeah, and the last one here is just the plot of the force and deformation relationship. I think, yeah, just to make sure that the energy dissipation and everything that we set out in our specification can be met. I think that's all my part. And we'll hand over to Bill.
Cool. Thanks, Jack. I've watched that video many, many times, and I always wonder, is it going to break this time? But it never does. Okay, so I'm Bill, and I'm part of the Road Lab team and the lead superstructure designer for the Parahaki Bridge. I was asked to reflect on what's the most difficult or challenging part of the design. And I've got to say, it must be one thing, and it is the interaction between the permanent works and temporary works. I just want to do a quick population survey. Who here is in the consultant space? Okay. And the construction space, contractors? Right, okay, I'll just have to watch what I say. This presentation isn't going to have all the details or include everything, but I just want to highlight the complexity of this interaction. And for a successful project, this is critical. So this bridge is built by the balanced cantilever method. In general, it's just we're starting construction from the piers, and then we're building segment by segment in balance. So just to walk you through the construction sequence, first the substructure is completed. Then we construct the pier diaphragm as well as the southern end span. So this portion of the bridge has to be built on false work because structurally the end span is usually longer than the cantilever of the bridge. So these can't be built in balance. Then we move on to building the segments, and these are cast in situ. The orange frames over there are what we call form travelers. So these are fixed into the bridge deck with these outrigger trusses, and that supports the concrete. Once you pour the concrete, you then launch your form traveler to do the next segment, and we are doing it in balance. Do that a few times, then you come to meet your land span, and then you do a closure pour with a closure restraint. So this closure restraint is really important because if you have any relative deflection of the two tips, then they can really damage your reinforcement bond with the concrete when it's still young. And congratulations, you've completed your first span. Just 3 more to go. And for the rest of the construction sequence, it's quite similar. Segment by segment by form travelers. You come to the closure pour, do that. And for the final span, there's also a end span false work. And then the closure pours are done. and the final closure pour is done, and then well done, you can crack your bottle of champagne. So I want to focus on two key components of this construction methodology and some of the temporary works. So the two I want to talk about today is the form traveler and the end span false work. So this presentation is looking at how the design evolves and what are some of the interactions between the permanent works designer and the temporary works designer. And it might be old news for some of you who has designed multiple box girders, but hopefully it gives you an insight of what are the key considerations when you design your first box girder bridge. So for the form traveler, the concept assumption is pretty simplistic, just a simple shape and a assumed form traveler weight based on a proportion of your maximum segment weight. When it comes to the preliminary design, the designer will be thinking about what's the post-tensioning layout, what's the SLS and ULS design criteria, not only for when the bridge is in service, but also when the bridge is under construction. This bridge is also a variable depth box girder, so it means that it's deeper at where the pier is, and it slims down to just 2.5 meters, almost half the depth at midspan, and really gives a very aesthetic look to it, as well as some structural benefits. We'll be looking at how the web thicknesses may need to transition and how all these geometries have these confirmed. And with this information, the form traveler designer will be able to look at various features of the form traveler. For example, with this variable depth, how will the formwork allow for these changes? And maybe there could be a change in the form traveler weight. And one of the interactions that we looked at, one of the value engineering exercises we looked at from early stages was, could we reduce a program by reducing the number of segments from 10 to 9? It might seem like quite a simple change, but it affects the segment length, the segment weight, the form traveler weight, the post-tensioning layout, and everything's connected. So when we're looking at these early optioneering stages, it's really important that the bridge designer and the construction team and the temporary works designer work very close together. Okay, so it comes down to detailed design. The bridge designer will be looking at confirming girder geometries, confirming the construction sequence, every pour that's made, every stressing operation that happens will have to be modeled in a structural analysis software. Then we also produce reinforcement details and looking at how to control the deflection of the bridge when it's being constructed. And with that finalized, then the form traveler designer can undertake their detailed design. Now, this is possibly the most difficult part when the design requirements of the permanent works and the design requirements of the temporary works conflict. For example, one of the key items that's still missing in the detailed design is how is the girder going to resist some very localized loads from the form traveler? And this information we don't have until the form traveler design is completed. So over here is a screenshot of a 3D plate model trying to assess the effects of the localized loads on the box girder. So the form traveler designer's design criteria is that the support on the bottom flange has to stay at the same position. Otherwise, it compromises the form traveler weight and the complexity of the form traveler. Whereas for the bridge designer, since the box dimensions are always varying, we have the reaction points being quite different for each segment, as well as the bottom slab getting thinner. And it was just no chance for an 800 kilonewton load to be resisted by a 250 thick bottom slab. So this is just an example of how complex it could be trying to thread a needle between design criteria. Eventually, we're able to find a solution that works, installation method for the load to be shared between the top and bottom flange. And I'm sure Sam will be quite excited for when these form travelers will be installed. These are just shown on the ground for now. I hope it outlines the complexity of this interaction. I think often it feels like a game of guess who. When you're sitting on the other side of the table, someone else knows the information that you want. So being able to ask the right questions is really an art. I know the analogy kind of breaks down because you don't want the other person on the other side to win and you don't want them to figure it out, but this is the nature of things. We have to be able to interact with various parties. Okay, and I want to talk about the in-span false work because I think it really shows off where value engineering finds a better outcome. So the question here is, we've got our balanced cantilever construction with the form traveler reaching out as far as it can go, but then there's still 17 meters that needs to be constructed. And how do we do that? It was a big challenge because we have a 15-meter cliff in front of abutment B. I know it doesn't look like much in the sketch, but some photos from site. This is the abutment. This is a few people working on the abutment, and that's how steep it is. But you're really already, there's another 2/3 of the cliff that you can't see from that picture. So it just gives you a bit of scale on the issues that we're facing. So from conceptual design, we thought, what if we continue building this bridge via a cantilever method, but prop it at the bottom to take out the out of balance forces? We did find that it needed some complex articulation because we wanted to hold it up vertically, but we don't want it to attract any seismic loads. And also we found that we needed a lot of additional reinforcement in the top flange to hold that cantilever. When it came to the preliminary design for the temporary works, they also found quite a few challenges. There is a railway that runs next to the prop, maybe 10 meters away. So needing to design for that collision load in that prop was quite onerous. And additionally, there was a cost to program because we still needed to build out 3 segments in cycles. So I got to give credit to our temporary works designer because sometimes coming in with fresh eyes, you're able to see options that haven't been discovered previously. So this resembles a bit more of a traditional false work, and the temporary works designers were able to find a solution to build false work even on the 15-meter cliff. It has quite a few benefits. For example, we can now build those end segments prior to the balanced cantilever being constructed. And I'm sure Sam's going to touch on it in his presentation. And also has reinforcement reductions. This is a picture of the southern end span. We haven't, the northern end span is at the end of construction, but we're hoping that we'll have a similar false work system to this. Okay, so the last part of my presentation is about geometry control. we're looking at constructing a span of 88 meters, and it's possibly from this wall to the other end of this office, maybe more. But the construction tolerance we were talking about is 30 mils. So that's for span to tolerance ratio is 1 to 3,400, which is quite tight. And at the same time, we are facing quite a few uncertainties in terms of how the bridge behaves. And having a misaligned tip is probably the worst nightmare for building a balanced cantilever bridge, because you're not left with many options. It's either you force the tips together and causing a large locked-in stress, or you try to fill it up with leveling course, which increases the weight of your bridge. So this is critical. So the uncertainties that we face include variability in concrete properties. As you know, concrete will creep and shrink over time. Also temperature. For the maximum bridge manual temperature loads, you could see your tip go up and down by 50 mils. So being able to survey at the right time, at the right temperature is really important. And then there is what is actually assumed on the deck, is how much plant and equipment is actually on there that could affect your geometry control and everything else. So what are the things that we can do? First is to be able to model each of your construction stages accurately in terms of duration, your concrete properties, and when tendons being stressed. And also being able to look at the conditions on site and see how the bridge is behaving. And for every segment, you have an opportunity to adjust your bridge geometry. So it's very much a moving target and something that you have to manage. And at the very end, there's ability to align the tips, but only a marginal amount. Obviously, we're not there yet, but I'm sure we'll have a lot of lessons learned when it comes to it. So that is my presentation. I'll pass it on to Sam regarding the construction aspects.
Good evening, everyone. So yeah, my name's Sam Couch. I'm the structures manager down at Turanga. So I have the pleasure of spending most of my week down in the Manawatū, and going to share a bit of a construction update this evening, just in general. But yeah, maintain focus really on Bridge 3 and Bridge 2, which we've heard about already. So just, I guess, a bit of an overview. There are two significant structures on the job, which is 2 and 3. But there are a number of other minor structures which have actually gone really, really well. Most of them, with the exception of Bridge 7 down in the bottom right, are very much nearing completion. Bridge 1, 5 and 10 are effectively box culverts. There are some complexities around them. 2 are single barrel, 1's double barrel. And then lastly, we've got Bridge 7 Mangmanaya, which is on top of an MSE wall. We've got some bank seats, and it's a pretty simple 30-meter span Super T bridge. I guess just before I kind of move on to the next bit, a lot of the photos I've got here this evening and some of the content have come from my team. So I'm trying to, I guess, hopefully do them justice and show the hard work that they've been doing down there. So yeah, just really thanking my team for the content that I've got here. So this is Bridge 2, Parahaki Bridge, or Manawatū River Bridge as it was known when the project started. So we were fortunate enough to have a drone fly over about 2 weeks ago. So these are pretty up to date. There's a few things changed since then. We've got the southern abutment in the foreground. The abutment itself is pretty much complete. You've got the southern land span, which Bill just pretty much talked to. You saw some photos a second ago of the false work in and underneath that. 4 lifts in that. We pour that floor diaphragm, walls, and then roof. So it's a pretty simple form of construction. It's about 14 metres long, and it's on that false work system that we will hopefully copy and paste and take to the northern end. So it's an opportunity, value opportunity, to take that false work from the south over to the north. You can see the 3 piers, one bordering either side of the river and one slap bang in the middle of the river. It's called Parahaki Bridge. That's Parahaki Island that you can see that the pier's just on there, and that's the Manawatū River. And looking away into the distance, you can just see Bridge 3 disappearing off up the hill. So this is quite early on in the alignment if you're coming from Ashurst or Palmerston North. And the historic road, or the old State Highway 3, you can't really see because we've kind of borderline buried it, but it just disappears off in the bottom right-hand side of this photo and goes underneath where that southern land span is. This is just another quick photo looking up the river. So you can see State Highway 3, the old State Highway 3, disappearing up the gorge. Got the quay rail corridor on the left, which is one of our challenging obstructions in the area. You've got the river itself, and you can just make out one of the biggest slips just up the river there on the right-hand side, which is completely buried that road. So that road's pretty much shut off, but you do get people walking up there. So it kind of gives an idea of scale. One of the kind of big focuses when this bridge was designed was to try and avoid as many piers in the river as possible. So you've got that one slap bang in the middle, but the other 2 are just right on the riverbanks. And you just saw this photo a second ago from Bill. Pier 3 is in the stage of the penultimate pour, so we hope to have all piers complete by the end of this month. One thing that Jack Chai touched on, which has caused a few challenges, the quay rail corridor meant that the pier relative to the pile cap had to be rotated relative to one another. So the reinforcement effectively rotated as you came up through the 3 metre height of the pile cap by 39 degrees, which is an interesting number. So you can kind of see there in the image, I guess this challenge or this change did present a few problems for us. Each pile cap's about 588 cubes of concrete in each one. It's poured in 3 lifts. Part of our challenges, which you can already pick up on, is how do we go about building a bridge like this? How do we get access in? We've got the riverbed itself. There's some cultural anomalies that were picked up through GPR survey, so we can't go through certain areas of Parahaki Island. We've got the river itself and quite a big interface with the river. The river fluctuates hugely in height at periods of high flood events, and you'll see a bit of a photo later. So it picks up the Hawke's Bay catchment area. We've also got steep slopes either side and just generally challenging ground conditions around the area. So very important when designing a bridge like this to consider what our access is going to be like for all that kind of equipment. Some of the other challenges, there were quite a lot of clashes with the reinforcement. You've heard that the reinforcement content is huge in all elements of the structure, and that's definitely not an understatement. It is absolutely massive. And what that does is it places a huge focus on temporary works, setting your reinforcement, making sure that you've not got those bar clashes. Otherwise, you make your life a lot more difficult for yourself as you progress. Being in a river, you also have to work generally inside a cofferdam. When you've got very long bars, which are quite large in diameter, splicing them isn't really an option, so they have to be continuous in length. And then how do you get long bars when you've got sheet pile wall either side of you? So that presents, well, couplings is one option, but it's certainly a very expensive option. And then removing things like hook terminations and putting couplings on so you can drop bars in over the top of pile cages, which is straightforward. We've got a very good team down there, lots of innovations, working very closely with the CPS team. So Hunter, I can just see his face here on the right. Hunter's been really key down on the ground there. He's helped work through a lot of the challenges on the ground, put forward some really practical solutions with the team, and some of the innovations are definitely a function of kind of the input that he's had with the Bridge 2 team. big innovations on the pile caps themselves. We had temporary works to support the starter cage. The starter cage for the piers is pretty significant and cannot support its own weight, and that has to suspend that cage partway through the paws. IMBMS couplers to support braking bars in lieu of the hook terminations, and then prefabrication of the components, and that's really to drive time and quality on site and maintain continuity of fixing. A few photos kind of demonstrating challenges with access. So right from the beginning, it was chosen to stage across the river. I know Penlink just up the road is following a similar type solution in stages. Ground conditions, ground's pretty crap either side. So soil nailing, quite significant soil nailing in this case. This is at the south abutment, sorry, just below the south abutment at Pier 1. And then it's getting into each of these areas at all stages of the weather. So you basically have to get your staging in right over the top of each pile. So if the rain comes and the water levels rise, it's not going to stop you working. So there we are. You can just see the access over the top of Pier 1 to put the piles in. Same at Pier 2, access in over the top of the cofferdam to put the piles in at Pier 2, and Pier 3 was much the same. And why is the staging 6 meters above the river when it's such a wide river? Why have we got a cofferdam at each end? So some of the time it is pretty dry through there, but then you get events like this, which is at the back end of Cyclone Gabrielle. So this was the highest the water recorded on site at the time. It did overtop our cofferdam. You can see the debris that came down from the Manawatū River and piled up against the staging. So the team regularly has to go through, move logs, timber, rubbish, cows out of that material and get rid of it. So days like this can be pretty destructive. And after events like this, you have to go in and do huge inspections on all of your temporary works, all of your staging through there, lift it up, inspect it. Your scaffold, you have to go down, clear around the bottom. So working in some pretty horrible conditions with the sediment down there as well. Innovations, just moving on into the pile cap that we just talked about, kind of thinking about where we're placing our hooks, how do we get in to construct the works. Again, a lot of this is worked through with the likes of Hunter and the team on site. So in the top left there, it's just an image swapping out the hook terminations at the top of the piles with couplings, so you can slot the prefab bar groups over. So in the top right, you can see the prefab bars dropping in. You can kind of get a gauge on the quantity of reinforcement in that pile cap. The right kind of diagram up there, you can see replacement of candy canes at part height. And that's so we can get in and create a type B construction joint on each of the lifts. So if you've got Rio right in around you, you can't really get in to do your construction joint. So they're kind of little innovations and little thought processes that happen on the ground that have been accommodated with the design. Bottom right image shows the temporary works required just to support that starter cage. This is actually in Pier 3, so you can see in this image the rotation of the pier relative to the pile cap. So the bottom mat was in one orientation, and then as we progressed our way up through the pile cap, the bars aligned then with the pier. 39 degrees is a key number because what that means is every single bar mark is different. 45 degrees would be better because at least it's symmetrical, but 39 degrees makes every single bar mark different. So, you know, this is one example, and I guess the shape, which will be a common feature throughout this this session, has a big impact on bar marks. One roof slab had 5,000 bar marks on a box culvert, so yeah, it can be quite a significant impact. And then just a pretty cool photo of one of our pours at night just down on the pier. Moving quickly on to the pier columns, 25 meters in height. It's the biggest one, as Jack Chai said. And they're hollow pier columns. Top 2 meters is a big solid mass, and that's to accommodate, I guess, some of the load transfer and the connections with the lead rubber bearings. We had a custom jump form system. It's a very unique shape. There's that word. So shape is a key function of some of the challenges we've had right the way through. The radial edges and I guess the density of reinforcement relative to that shape has proved challenging. There is a mahi toi relief pattern cast in the sides of the piers, which is about 50 mil deep. That's actually been a bit of a saving grace. That 50 mil has provided us with some cover tolerance on the radial sections of these piers with the density of reinforcement we have. The shape has led to, I guess, bespoke molds, so we can't use formwork systems, or we have to modify formwork systems. So that just adds, I guess, a bit of challenge there. Access, feeding bars in, using a jump form system is great, but when you're trying to feed bars in all the way around, you don't often have access. So we ended up scaffolding around the whole thing, and that was actually far quicker than trying to use a jump form system. So the cost of scaffold versus just providing better access make that well and truly justified. We prefabbed huge sections of reinforcement and then knitted them together around the radial sections. The biggest portion, I guess, of in situ Rio tying as you got to that kind of section right up the top form. Creating the void was fairly straightforward for the straight sections. We just jumped a form up inside the pier, and then a really good innovation on the design with the temporary works team is we cast in a precast box in the top lift because the void terminated partway through the final pour. So we hung the box within the structure after the fourth pour, and then on the fifth pour or sixth pour on one of the other piers, we just cast in a precast box as leave-in place formwork. Left-hand Rio model, we've done a huge amount of modelling with silicon for the reinforcing just to make sure everything can fit. That's just an example of it on the top left there. And this is just what it looks like in reality. So left image there, the people are there for scale. They are full-sized people. Yeah, there's a huge amount of density and reinforcement. When you've got a shape like that with limited access, getting that shape right is really important. You've got surveyors with a model within their instrument actually surveying every single bar to get that bar right. You struggle to get, where do they survey on that radius? Where do they put their instrument on that bar to make sure you've got the shape right? And what are you building your reinforcement off? So setting profiles up, that complexity again. And then you've got a heap of embedded items within the top as well, in the form of your sole plate connections and your bearings. And then looking into the corner, so this is kind of the radial section of the termination of the pier, where you've got all of the hook terminations. This gives you a real idea of density of bars, so 25s, 32s, and 40 mil bars in this section. And then you've also got your embedded items, some of which go 1.2 meters down inside that pier. So gives you an idea of the kind of congestion. Then biggest problem then is how do you get concrete in through that? So we use a self-compacting concrete. We had steel forms for the top section, had ports on the concrete, did a trial pour, and really critically analysed how we were pouring the top of this pier head. We're very, very concerned about achieving the slope on the top with a self-compacting mix. There's about 300 mil crossfall on the top, and self-compacting mixes tend to like to stay flat. So yeah, big challenges, but actually all three, because we were conscientious about it, have all gone really very well. Or the two have gone very well, and we're just coming on to the third one now later this week. So as part of the interface with the lead rubber bearings, they sit in pairs. There's 6 of them in total on top of the pier. They sit in pairs on top of these sole plates. Sole plates connect into the rear of the top of the pour with about 300 mil embedment. So you can't pour that with the in situ concrete. You have to pour that with a grout or a micro concrete. It's 300 mil thick, which basically rules out most grouts available in New Zealand, or certainly a lot of them. And as part of the process, we have to do a glass plate trial to ensure we get 90% coverage underneath that sole plate, because you can't see through the steel. So you do it under perspex, and you can't have a void of more than 50 mil. So it's pretty challenging to be able to achieve that, and you have to prove that in advance. 8 trials were undertaken. The cost of a glass plate trial is about $20,000, so they're pretty expensive. And one of the challenges with them is because the grout isn't available in New Zealand, you need to bring in significant quantities to do the trial. And then if the trial's not a success, you either have to scrap the grout you've ordered, or you have to go and procure another amount, most of which comes over from Australia or the US. But the positives, we did replicate site conditions as far as possible. So that's that top left image. We found the best solution was 4 ports on the short end, not on the long side. We angled them slightly up towards the plate, sealed the box except for the outer end, and allowed air through the other end, and then over poured quite significantly to get it out through. Other key was good quality micro concrete. We tried a lot of concretes or grouts available in New Zealand, and we couldn't achieve the specification. They were far more susceptible to changes in moisture content. So yeah, just those are kind of some real good learnings, and certainly if you're looking to replicate that anywhere else, yeah, we went through a lot of pain to get to this point. So definitely feel free to get in touch. Availability of micro concrete still a significant issue. We basically exhausted all supply in Australasia of that product doing these samples. But overall, really good outcome. The trials meant that when we did it on the ground, it was a great success. So. Onto the pier table quickly. So pier table or hammerhead, there's a portion of superstructure, including the diaphragm on top of the pier. It has the terminations for the continuity PT, which supports the spans. Those are these kind of radius tubes running through the diaphragm that you can see in the image there. All of the cantilever PT, which links segment to segment, also passes through the top flange. It's again, shape is a big challenge. The soffit of the bridge is not flat. It's got a bend in the middle of it. It's also on super elevation and gradient coming from each one. So what that means is there's no common RL anywhere on the bottom of that soffit. So it's all very, very custom. But the main benefit is each pier table is the same. So once you've done it once, you can just copy and paste it onto the next two. So challenges, shape, survey requirements, reinforcement. Again, bar marks is a big problem. Tolerances, modelling, every single bit of Rio needs to be modelled, and it's modelling not the theoretical Rio, it's modelling the Rio and factoring in the code tolerances. So what can you achieve with your bar bends, bar placement, bar length? That's really, really important because it might work in theory, but in practice, we're kind of rebending a lot of bars to try and make it work. Lifting capacity intensity, just considering that through the construction methodology. We've got a 280-ton crane there with super lift on it, and that's just to lift a 20-ton load off the far side, just taking out the formwork. So it's really important that's kind of considered right through the design process, and certainly considering the size of your elements, size of prefab reinforcement cages, and what your temporary works looks like right through those early stages. Temporary works and permanent works, kind of talked to that already. It's just led to a lot of congestion up through the structure. We transfer the load for this element down through the ground during construction, and this element up on the top is ultimately what the form traveller sits on and starts its journey out for each segment. So we've actually poured that second lift, which was in that top image there. We're prepping the third lift, 3 lifts in that pier table. That pier table should be complete by the tail end of next week. So that's 1 of 3 complete. And then we'll begin the journey of stripping that and chucking the formwork onto the second one. Yeah. Superstructure segments cast monolithically, so land span, floor, diaphragm, walls and roof. The segments are poured as one, so they're poured from the top. There's a pour methodology. We've done some trials on site. Ultimately, you have to pour your bottom of your walls and your floors, then your walls, and then your roof, and then you go and do the other side. There's about 80 to 100 cube in each segment, and then you start the journey all over again. You stress it to the next one, and then you carry on. Big permanent works and temporary works interface in terms of embedded items. That form traveller has a lot of embedded items that run through the previous segments in order to progress. It runs on a set of rails. You've also got a load of bars penetrating through the deck, support your internal soffits and the ability to roll them forwards. And when we're designing Rio, it's just how do you get your Rio in there when you've got that amount of temporary works hanging over the top of you. But on that, I guess innovations, because this really does drive your program in a balanced cantilever method, making this method as efficient as possible is really, really quite important. pre-assemble as much as possible of the form traveller, prefab the Rio, modify your form traveller where possible to get as much prefab Rio in as possible. And then your concrete mix is really key, because curing time overseas might not be so much of a problem, but achieving kind of 30 MPa within 24 hours here can be a problem, especially in winter in a very windy area where the weather can be pretty bad. So insulating the mold was probably the biggest lesson we've taken from talking to a load of people here and overseas. And then the shape problem again, so that in the red box is a typical cross sections of the bridge. So that's for the entire bridge from the design pack. So three drawings. Because of the complex shape, the modelling and the interface with temporary works, including penetrations, which you can see down the bottom right. Of the 27 segments, we have to produce eight drawings through models in order to be able to build a segment. So it's really important getting that done up front. I think from certainly from a constructor's perspective, and I know we've talked about it with my colleagues here. Like, if that can happen early days, getting that modelling done, it just speeds up the whole process later on and resolves a whole heap of design clashes with reinforcement. So. Program, very critical. This is a typical cycle time of a pair of form travellers. So a form traveller sits up on top, you've got an upstream and a downstream section. It's an 8-day cycle time in theory. You've got concrete curing in the mix there. So making this as efficient as possible is really key. The little boxes highlighted in red, but with the green little squares in them, reflects 20 hours of fixing time to fix 22 tons of Rio per segment. That's incredibly tight in a congested site area. So prefabbing as much as that as possible was really key. I guess all I've chucked this in for is just, we use this as time chainage. It's linked to the program, linked to the segments and construction. It's just a really good way of us picking up where we can improve and make efficiencies. The gaps are things where we can buy things like additional temporary works to speed it up. But ultimately, as you work through it and reduce those gaps as you progress through development and procurement, the only thing you can really do to speed up your program and ultimately deliver on time is reducing the size of these little boxes there, which is linked to that cycle time. So curing, reinforcement, prefabrication, and progressing that form traveller on a repetitive but short duration. Cool, so that's bridge 2. Just touch on bridge 3. Bridge 3, obviously Jack's touched on a few details around challenging ground conditions and kind of highlighted that an aquifer or artesian water pressure might have been an issue, and it certainly was. This just really goes to show the status of this bridge at the moment. So bridge 3 is progressing incredibly well. We've got 4 spans in place of 7, so 3 left to go. All of the columns bar 1 are complete. Both abutments are done, and we'll be landing precast in the next kind of couple of weeks. So this bridge is a big success story, I think. Like, the team have worked incredibly hard to get to this point. And these beams are just made out of East Bridge in Napier, and were delivered as brace pairs. So brace pairs on the 47 metre span are 100 tonne, so pretty significant loading. There's the pier head, the integral pier head that Jack pointed to. So I think you can probably all agree it looks really good. It's a very slender structure. Quality of the finish is good, I think. But yeah, boy, were there a heap of challenges in that. So shear studs for one, quantum of reinforcement, shape is a big challenge. Looking at the end radius on those pier heads, that certainly made the congestion and the bar bending tolerances another challenge. Yeah, but I think just in general a really good outcome. So onto the, I guess, artesian water pressure. So Jack talked about limited GI right through the early stages. It identified 3.5 meters above ground level artesian water pressure, which is, it's artesian water pressure, but it's not huge. But as we went through the ground investigation, or tried to do ground investigation in the early stages, Sue found that we couldn't conduct the ground investigation because artesian water pressure was an issue. So there's some proposed locations abandoned at 15.9 meters deep, artesian groundwater, abandoned at 19, and abandoned at 13 for artesian. So the ones that were undertaken couldn't be conducted because of artesian water pressure. So tender, 3.5 meters above ground level. Original GI, 10 to 12 meters above ground level, but unsure because they couldn't reach that deep in the ground conditions. But the revised ground investigation in 2021, 23 to 24 meters above ground level. So significant artesian water pressure. Piles going 23 meters deep and 36 meters deep on the large on the others. So 23.24 meters, there we are on the investigation. So significant groundwater pressure, showing the need that we needed to dewater it, drill under fluid. So in this instance, we drilled under bentonite and had to dewater the entire field. The little graph on the right there just shows the monitoring that was undertaken the entire time. The solution that was implemented needed to be something that we could do quite readily and run basically for 6 months for the piling duration. So what did that artesian water pressure do other than change the pile methodology? The intention across this wetland was to stage across the wetland. If you're staging across the wetland, the problem is you're punching lots of little holes into the aquifer, which is not a good idea, which meant the design for the access had to change to a fairly significant causeway through the wetland, avoiding these kind of really sensitive wetland areas, which are shown by those little cross box outs there. And we've got native forest either side. So it's an incredibly sensitive environmental area. Pretty significant numbers, and there's a bit of a cross section showing what the causeway looked like, but significant volumes of undercut, significant volumes of cut to waste through there, and a lot of geogrid. But fortunately, I guess good outcome is that's now going to remain in place and be a wetland experience through at the end of the project. So it's utilising that temporary works through there. And just a few photos showing kind of construction of the causeway as it progressed. But yeah, pretty significant in size. So just down the tail end. Heaps of geogrid and geofabric. Lots of river run, conglomerate, gap granular material, but then a pretty nice outcome overall. And now that grass has all kind of grown up and the native forest has been rehabilitated. So lots of pest control and ecological control going on in the area. Just quickly touch on piling, put 6 meters casing above ground level. Following the revised ground investigation and dewatering, piling actually went really well. We did 15 piles to those depths noted, so 36 and 21 meters roughly within 4-month period. So generally a really good outcome overall, and the columns progressed pretty quick afterwards. Now this wasn't so much a challenge, but the columns was actually a great outcome. When asked for rate of rise on the columns, we just said as quickly as possible and designed the temporary works accordingly. Went through a process of doing concrete mix selection using that self-compacting concrete again, but the cycle time overall improved really good. We spent the money on the temporary works, poured them really, really quickly. And I think like just the concrete finish on these things overall is absolutely fantastic on every single column. So we haven't had an issue on any of the columns. So just a bit of a good outcome there. Pier heads, just conscious of time, but pier heads were fully integrated. So integral pier heads as part of that low maintenance design and aesthetic. The biggest challenge from a construction perspective is the girders, which are fairly significant, 100 tons in braced pairs, so 300 ton per span. Need to be supported while you're pouring the concrete. So it needs to support the concrete, the Rio, the girders, and construction loading there as well, and provide reasonable access. But down below, you've also got a wetland, so you can't put foundation for that temporary works to the wetland. So what that means is you ultimately need to drop them down onto the piles themselves or to the bottom of the columns. And we ended up with this solution that was worked through by the temporary works team, transfers the load straight to the pile casing. Didn't need to touch down in that wetland, met the full weight, and and the designs were kind of customized, those kind of dark grey sections in the right there, so that they could be jumped and reused peer to peer. And they've gone really, really quite well. Looking at them up in the air, you wouldn't kind of think they're going to support all that weight. There, I can just see them being lifted up. But yeah, you certainly wouldn't think they're going to support that weight up in the air, or they'd move or displace, but they're tied back to the piers, provided some really good access, didn't disrupt the wetland. So this is our yard, but further back in the picture, there's a significant wetland area. There's an aerial view showing them going in and taking the beams. So 100 ton, as I said. One of the challenges around that integral pier head and the kind of Rio working the way it did is you had to phase your Rio installation. So base Rio, dropping plates on with studs on, dropping the beams over the top, bolting your base plates to the flanges, and bolting your webs together as well. So quite a significant amount of work in quite a tight sequence, and with a huge amount of congestion. But outcome, based on that photo I showed you at the beginning, really, really good. And the team has done an incredible job down there. Just a few last photos going through. So I guess just to summarise, not just from myself, but from all of us here, the effective solutions that we have presented have required really collaborative engagement between the permanent works and temporary works designers. And I think as early as possible as that can occur, not at high level concept stage, but actually diving down into the detail, in particular like balance cantilever and the false work for bridge 3 on the beam connections is really, really key, and just streamlines the whole process. Going through that robust optioneering through that early stages of design, and yeah, progressing both designs in parallel, not permanent works then temporary works design. So yeah, that's certainly it from me and my colleagues. I think we're taking questions now, I guess. Yeah.
Maybe if there's just a couple of burning questions, otherwise we'll close up. One burning question. Anybody? There was one online. This one's for Bill. Can you please explain how to verify the secondary effects of creep and shrinkage, thermal effects, and stressing? Thanks.
So in terms of the concrete properties, we've done quite extensive testing. So in terms of the secondary effects, we've done a 56-day shrinkage test. In terms of temperature, I think probably the most useful information is to survey the temperature at the top of the deck, the temperature at the bottom of the deck, and see how that affects the structure over time. So you really see the real performance of the structure. Yeah.
Any last questions? No, otherwise we can just thank our presenters again. There was a question, is Parahaki Bridge the first bridge in New Zealand to use base isolation?
I do know that there are a few buildings that are base isolated. One is in Wellington, but for the bridges, this is like a game, guessing game. Yes, I think so, but I'll confirm that later. I think, yeah, we are the first maybe to use the base isolated structure. Yeah.
One last question from Hunter. Wondering, this is for Bill again. Wondering, have we ever considered the possibility to use vertical post-tensioning bars for web shear?
Vertical
PT bars?
No.
Cool, thanks. Okay, if we can just thank our presenters again, and then we'll close up. Thanks.